Hi, it's Mr. Anderson, and today I'm going to talk about solutions, and then I'm going to show you at the end how to calculate molarity. Now, normally people think of solutions as, for example, this can of Mountain Dew, or maybe water, a glass of water that you add salt to, and that's a solution. But solution is essentially two or more substances that are really mixed together at the molecular level. And so that definition actually applies to a lot of other things. And so air is actually a solution. And so in any solution you have the dissolving material. In this case it would be nitrogen gas. And then what's it dissolving? It's dissolving everything else. And so it's going to mostly be oxygen, but it's also a little bit of argon and some other trace elements. Or like steel. The steel cable right here is actually a solution or an alloy. What is the solvent? In this case, the solvent would be iron, but it's also going to have little bits of other trace elements, like carbon is one of the big ones in steel, which actually keeps those iron molecules from sliding past one another at the molecular level. And so that's a solution. Another good way to talk about what a solution is to talk about what isn't a solution. And so there are two things that sometimes can trick you up as far as solutions go. First one is something called a suspension, and the suspension actually is heterogeneous, so it's not mixed together at the molecular level. This right here is a picture of flour that's been added to milk, and then you stir it up and you have a, not flour and milk, but rather flour and water. You mix it up really, really well, and then you have something called a suspension. Now if we let it sit long enough, that flour is eventually going to settle out. And that's one of the defining characteristics of a suspension. If you let it sit long enough, it'll eventually settle to the bottom. So like muddy water would be an example of that. Next group is something called a colloid. And colloid is something that most people have never heard of before. But you've definitely drank a colloid before, and so milk could be an example of a colloid. A colloid is going to have much smaller particles, but if we zoom down to the molecular level, you're going to see that, for example, in milk there are going to be big fat globules, there's going to be proteins around the outside, and so it's not going to be dissolved to the level of a solution. Now you might think to yourself, how could I even tell the difference between each of these? And so one thing that we use sometimes to delineate that is something called the Tyndall effect. And the Tyndall, I'm sure, was named after Mr. or Mrs. Tyndall. But the way it works is this. You take something like a laser, but any kind of light would work, and we're going to shine it in this direction. But if you've ever shined a laser, you'll notice that actually in the room, which is a solution, you're not going to be able to see the laser. And so as we shine it in this direction, you won't be able to see any of the light. And it goes through a solution. Let's say this is maybe some salt water. You're not going to be able to see the light as well. But when it enters into the colloid, you'll actually see that light. And so this picture over here is actually light coming in, and there must be dust or something in the room which is creating a colloid, and then you're actually seeing this Tyndall effect as it comes through. We'd also see the Tyndall effect in a suspension, and in fact we might not even be able to see it because there might be big enough particles that it actually blocks that right here. And so again, a good way to tell what's not a solution is to shine a light through it, and if you see the scattering, then it's going to be a colloid. And if you don't see anything, that means that it's dissolved so well that it's actually a solution. So what is a solution? A solution is a mixture of two or more substances that are homogeneous at this level. And so right here we're actually adding salt to water, and that sodium and chloride ions are actually going to be surrounded by water to the point where they're thoroughly mixed. If it's completely surrounded, then it's a pure, we would call that a pure solution. Okay, so water is sometimes referred to as the universal solvent. How does that actually work? If you look here, this is that salt water I was describing just a second ago. And so this is the sodium and the chlorine ions, so this is a cation and an anion, and when you add that to water, the water will line up around it, so all the positive hydrogen atoms are actually surrounding the negative chlorine, and vice versa up here. And so water's really good at dissolving salts. In other words, it's really good at dissolving compounds that are held together with a cation and an anion. It also is really good at dissolving covalent compounds as well. And so this would be sucrose. Sucrose is that table sugar, and we can add tons and tons of table sugar to water and it'll just keep dissolving. The reason why is these groups up here, this is actually a hydroxyl group, and that's an oxygen attached to a hydrogen. And so you remember that oxygen's really electronegative, and it's going to pull the electrons towards it, so it has a charge here. And if you look at all the hydroxyl groups around this outside of the sucrose, it's really easy to dissolve a whole bunch of sucrose in water. Okay, so what's molarity? Well, remember when we were talking about like solid amounts of an atom, we would use moles so we could actually use an amount in the laboratory. Well, when we're dealing with solutions, we have something that's based on the mole, and that's called molarity. And so what is molarity? If we define what molarity is simple. It's the moles of the solute divided by the liters of the solution. And so the higher the molarity is, the larger the number of moles of solutes are. And so if you're playing in the chemistry lab and you're playing around with like 0.1 molar hydrochloric acid, it's not very scary. But if you're playing around with like 10 molar hydrochloric acid, that's pretty nasty stuff. And so the higher the molarity number, actually the more stuff is dissolved in the solvent. So what I thought I'd do, since I always talk about Mountain Dew, is we'd actually figure out the molarity of Mountain Dew. And so I looked on the can and I found that in a regular can of Mountain Dew, there are 44 grams of sucrose, and that whole can, a 12 fluid ounce can, is actually 354 milliliters. And so what I'm going to do is try to figure that out. So I'm going to take 44 grams of sucrose, so that's the solute, and then I'm going to divide that by 354 milliliters of the solution. So I got to do a little bit of converting here. So I'm going to first of all convert the grams of sucrose to moles. So to do that, I'd have to figure out the molar mass of sucrose. And so how do you do that? Well, you have to add up the mass of the carbon, and not only one carbon but 12 carbons, the mass of 22 hydrogens, and the mass of 11 oxygens. And I did that a little bit a second ago, and I found that it is 342.30 grams. So for a mole of sucrose, you need 342.30 grams. And so I can just put this down here on the bottom. So that is 342.30 grams of sucrose in every 1 mole of sucrose. So when we're doing this factor label, I can cross off the grams of sucrose, and I've already converted it to moles of sucrose. I'm almost there. You'll notice that I have milliliters of solution here, but I have to get to liters of solution at the top. And so I'm going to use a conversion as well. I know that 1,000 milliliters of solution is equal to 1 liter of solution. And so what do I get when I take that? I'm going to take 44 times 1,000 divided by 354 times 342.30. Again, I did that just a second ago, and I ended up with 0.3633, but I'm going to stop there, molar solution. If we look at my significant digits, you'll notice that I have 2 significant digits here, I've got 3 here, and so the right answer equals 0.36 molar sucrose solution. You'll notice here when I write molar, I can just abbreviate that with a capital M. So that'd be a 0.36 molar solution. So that's a pretty ton of sugar in there. It's actually quite a bit of sugar in Mountain Dew. Let's go to another one, because this is the way you'll sometimes be asked this in a regular lab. Let's say we've got sodium chloride, which is going to be table salt. How do you prepare a 1 molar sodium chloride solution? So what I want to do is a 1.0 molar NaCl, Cl. And so what that is equal to is actually 1.0 moles of NaCl divided by 1 liter of solution. So how do I convert that? Well, I'm going to put 1 mole of NaCl on the bottom. And now I have to figure out the molar mass of sodium chloride. So I'm going to look on the periodic table. I find the mass of sodium. I find the mass of chlorine. If I add those two together, I get 58.5 grams. And so how would I actually make let me cross these off, how do I make a 1.0 molar or standard sodium chloride solution? I'm going to take 58.5 grams of salt, NaCl, and then I'm going to pour that into a beaker, and I'm going to add water until I have 1 total liter of solution. And And once I've done that, I'll have a 1.0 molar sodium chloride solution. So if you know anything about molarity, you could say, once I'm given the molarity, I could calculate how to build that, or I could go backwards. If I know how many moles in there, I can calculate the molar solution there is. And so again, molarity is simply telling you how many moles of solution are in 1 liter. And I hope that's helpful.